This is the part 2 of the video for class 9 for the topic gravitation. Here we shall discuss more about the gravitational constant G. So previously we had done till this expression F equals to G m1 m2 upon r square, where F stands for force between the two masses, capital G stands for the gravitational constant, m1 and m2 stands for the masses of the first object and the second object, whereas r stands for the distance between the objects. Okay, so this G is known as gravitational constant. The value of G remains same at all places and it is independent of the nature of the particles, temperature, medium, etc. Therefore, it is a universal constant and is known as universal gravitational constant. It may be mentioned here that force is a vector quantity. Hence, it is necessary to indicate its direction also. So, force is a vector quantity. So the direction of force F12, which was the force on the mass m1 because of the mass m2. So it should move towards m2 here in this figure. So this force, right? So this m1 because of this force should be pulled towards m2, and F21 here is force acting on this object here, and this one should be moving towards this m1, so they should collide with each other, right? So now we can go to this line. Both these forces are equal in magnitude. They will not cancel each other because they are acting on two different objects but opposite in direction. That is, F12 equals to minus F21. So here I would like to clarify one thing. This minus sign here shows me the direction of force which is opposite. Thus it is an action reaction force which is acting on two different objects. Remember, here calculations cannot be done taking these forces together, right? A particle exerts a force on another particle equal and opposite to the force that the second particle exerts on the first particle. Unit and value of the universal gravitational constant. Unit and value of the universal gravitational constant. Here we are trying to find the unit of capital G, and we are trying to find the value of this capital G. How much should it be numerically equal to? Okay, what should be the number representing this capital G? Because it is a constant. Constant means it should be a number. So from equation 3.12, this equation here, so from equation 3.12, this equation, we can find the value of G after cross multiplying it. Okay, let me show it to you all. So taking the value of force, which the previous formula, F equals to capital G m1 multiplied by m2 divided by r square. If I cross multiply this, so I shall get G m1 m2 equals to f r square, right? So now I can find the value of G. Which will be G is equal to f r square upon m1 and m2. Okay, this is how we are getting the formula for G. So let us go back to the page. Hence we have come to this formula here. G equals to f r square upon m1 into m2. So what will be the unit of G? So unit of G will be unit of force, which is Newton, unit of distance, which is distance into distance. Here r square means meter square, m1 kilogram and m2 is kilogram. So here the unit of G will be Newton meter square per kilogram square. This one here, Newton meter square per kilogram square. I hope you understood this. Now the value of G is 6.77 into 10 to the power minus 11 Newton meter square per kilogram square, right? That means this value is for two objects of mass 1 kilogram per kg. You can see here kilogram square means 1 kilogram and 1 kilogram, and there is 1 Newton of force in between them, and the distance is only 1 meter. So let me try to explain this. So the value of G becomes 6.67 into 10 to the power minus 11, right? It is given, this value is given in your book. So this value is true only for the two objects where two objects of equal size having 1 kg each, the masses are 1 kg, and the distance between them is 1 meter, and the force between them is 1 Newton. So whenever the force between the two objects is 1 Newton and the masses of each object is 1 kilogram, such that they are separated by a distance of 1 meter, then only the value of G here will be 6.67 into 10 to the power minus 11. So this is the value of capital G, which is universal gravitational constant, for the SI units of other factors, right? So let us go back to the page. Hence, gravitational constant G is numerically equal to the magnitude of force of attraction between the two masses, each of 1 kilogram, placed at a separation of 1 meter. Okay. Examples. Number 1, the gravitational force of attraction between two bodies of masses m1 1 kg and m2 is also 1 kg. Suppose two 1 kgs are separated by a distance of 1 meter, then what will be the gravitational force between them? So here we are trying to calculate the value of the gravitational force in space when two objects of 1 kilogram are separated by a distance of 1 meter. Two objects of 1 kilogram each are separated by a distance of 1 meter. So putting the values of G, so you know the formula of F, which is G m1 m2 upon r square. So value of G, just now we calculated it to be 6.67 into 10 to the power minus 11 multiplied by m1 m2, here 1 into 1, and distance is 1 square. Hence I'll get the same value, which is 6.67 into 10 to the power minus 11 Newton, which is very less, right? The value is very less. Now let us try to calculate the value of the gravitational force between moon and the suppose earth, right? Let us see. The gravitational force of attraction between the moon, whose mass is 7.636 into 10 to the power 22 kilogram, and Earth's mass is 5.96 into 10 to the power 24 kilogram, taking the distance of the moon from the Earth to be 3.80 into 10 to the power 8 meter. They are so big numbers, right? So when I put the values of these things in the formula for force, which is F equals to G m1 m2 upon r square, F equals to G m1 m2 upon r square. G's value was 6.67 into 10 to the power minus 11. M1's value, which is the mass of the earth, which is 5.96 into 10 to the power 24. M2 is the mass of the moon, which is 7.36 into 10 to the power 22, divided by the distance between the earth and the moon, which is 3.80 into 10 to the power 8 square. After doing all the calculation, we shall get 2 into 10 to the power 20 Newton here, 2 into 10 to the power 20. So when you try to compare these two values here, this value here and this value here, sorry, this value here. So this is very less compared to this here. So from the above two examples, it is clear that the gravitational force of attraction is significant between heavenly bodies, but it is insignificant, very less between the ordinary bodies. That's why we don't feel it, right? So now, in fact, regarding the gravitational force, it is important to note that the gravitational force between two masses, whatever we have studied till now, okay, whatever we have studied till now can be summarized as, number one, the force of gravity F, the force of gravity F, not G, okay, the force of gravity F is always attractive, it is not repulsive, right? Number two, it is directly proportional to the product of the masses. It is directly proportional to the product of the masses. That means it is significant in the heavenly bodies. Number three, it is inversely proportional to the square of separation between them. That means as the objects go far away from each other, the force of gravity between them decreases. Thus, by doubling the separation between the two masses, the force of attraction between them reduces to 1/4. This I'll show it to you when we are doing the numerical problems. How does it become 1/4? Next, number 4, it is significant between the heavenly bodies but is insignificant between the ordinary bodies because of small magnitude of G. The G is the value of capital G, which is the gravitational constant, is very less.